Hi everyone. In this work, we designed provably efficient policy optimization algorithm using Thompson sampling. This is work in collaboration with my wonderful collaborators Zoran, Andre, Viet, Luis, Riasat, Doina, and Zauran. Recently, DeepRL has achieved lot of success in solving complicated tasks such as AlphaGo, StarCraft, or solving Rubik's Cube using robotics arm. However, all this success come at the cost of a huge number of samples, meaning like it takes like days to train all this algorithm, and because of this huge sample complexity, it's still not feasible to use RL for real world problems such as clinical trial, self-driving car, and so on. And all these successes are achieved using policy optimization algorithm mostly, but policy optimization algorithm can fail without proper exploration strategy, even in the simplest environments such as combination log that we see here. Here, the huge reward is at the end of the right node x100. However, there are like small rewards in the beginning of the nodes, beginning of the chain. So if you go left, for example, in the beginning, you can accumulate small number of rewards. So it's natural that agent will avoid going to the right. So our goal is to design algorithm, policy optimization algorithm that will use Thompson sampling, and we can show probable regret bound and sample complexity. For theoretical purpose, we consider linear MDP where the kernel transition kernel is linear in the feature of state, action, and next state. So our goal is to estimate the theta star here via ridge regression. So to do this, we use this technique called optimistic sampling to achieve this Thompson sampling based exploration. So the main idea is that in Thompson sampling, you always want to show that your state action value function estimate is optimistic with a fixed probability. However, uh, analytically, it is challenging to show it, meaning like probably it is difficult to show. So to boost the optimism, we sample multiple noises and part of our estimated theta, and at the end, take max of those q hat hi on the right hand side here. So we basically take the max of all the part of estimate of q hat. We also showed experiment in reverse swim experiment environment. For example, we showed that our algorithm Thompson sampling with policy optimization, aka TSPO, performs much better than the UCB variant of policy optimization, OPPO, and and we also showed that PPO, which is without any exploration scheme, fails miserably here. And the most interesting observation we did was Thompson sampling algorithm, like in our case TSPO, is much robust to hyperparameter tuning, whereas UCB-based OPPO algorithm is not robust to hyperparameter tuning. And in the left, we can see that the performance of OPPO varies a lot when we change the hyperparameter beta, whereas on the right, we see the performance of TSPO is relatively robust when we change the sigma square, which is the posterior inflation parameter in our in TSPO. So in summary, we designed a probably efficient policy optimization algorithm using Thompson sampling, and we achieved a regret upper bound of d to the power 3 by 2, h to the power 3 by 2, and square root t, where d is the dimension of the feature, h is the horizon length, and t is the number of time step. And For more detail, please check our poster. Thank you.